Um, Hello, I'm Nikhil Tangirana. I work at DB. Yeah, so I'm going to be talking about a couple of rail station focused pedestrian simulation models we've created recently. So first, I'll run kind of quickly through the first two sections because they're more basic. But first, I'll just give a little overview over our pedestrian modeling process. So how does DB use pedestrian modeling for station planning projects? So the goals here are to bridge the higher level station planning process with a more granular on the ground passenger experience. It allows us to bring together outputs from our various analyses, including ridership simulations, service planning, and demographic analyses as examples in order to create more realistic representations of passenger behavior and station use. It allows us to validate our station designs, identifying any layout or process-related bottlenecks that can be addressed through design considerations. And then it allows us to predict any crowding and impacts on efficiency of boarding and alighting of transit vehicles, as well as passenger travel times and overall station performance. So briefly, the simulation process, again, kind of basic, but first step would be to define our objectives. What is our research question? What are we trying to achieve with the model? And then that allows us to proceed to set up the model, which is the actual nitty-gritty, coding in Vissim. And then running the simulation, which would be a more iterative process where we validate the model against real-world data. And then finally, we can evaluate the results with the variety of evaluation options that are available to us. So now just a brief overview of setting up a rail station model. So first step would be to build a station layout, incorporating the transit services that lay the baseline for our pedestrian models. So this is where we decide what are the actual areas that we want to model, like what are the areas of relevance in our model based on a research question, what are the points of interest that we need to model, so like do we need to show ticket machines or a business lounge or things like that, and then what is the transit service, so what service plan are we using, what are the schedules, those kinds of things. Next is the pedestrian inputs that populate the actual passengers in the model. So what are the volumes of passengers that we anticipate? What is the distribution of arrival times to the station, and how might that be affected by passenger types and passenger characteristics? And then also just what passenger types do we want to model? Like, do we want to look at trip purpose, like business passengers versus leisure passengers, or do we want to look at age? Like, do we want to be able to model how senior passengers might move throughout the station, etc. Next is the pedestrian routing. So this dictates this is based on the station circulation parameters, how passengers will access the platform, how they'll enter and exit the station, how they'll use vertical circulation throughout the station. And again, this will also be tied to pedestrian types and characteristics. And then finally is the measurement. So transit dwell times, level of service, queue length, things like that. So now I'll go into two case studies of projects that we've worked on. I was asked not to show the actual names of the stations that we worked on, which is why they're a little anonymized for the presentation. But the first station that I'm going to talk about is a legacy station expansion project, specifically for a regional rail station. So the research question here is just looking at, can the proposed station layout and operational processes handle the future projected ridership safely and comfortably? And for this model, the ask was to test out a high stress scenario. So For this model, we modeled 1 hour of peak service using the future station layout and transit service plan. And we assumed 120% capacity for the passenger volume. So 120% capacity of all the trains, basically. And this is to simulate a high stress scenario with elevated ridership. Might correspond to like an event situation, but this is basically trying to test the limits of the station. And for the evaluation, we wanted to look at metrics like platform clearance times, transit delays, or train delays, and then level of service and queue dynamics. So to set up this model, a few of the parameters that went into this. So for the station layout and transit service, the station layout was based on the future station designs. For the transit service, we used our projected or our planned service plan for this service, which involved 8 trains per hour per direction. This train is a terminus station, so travel is only in one direction from the station. For the pedestrian inputs, again, passenger volumes were set to 120% of capacity. We also modeled, or based on assumptions, we modeled passenger arrival times so that passengers arrived at variable rates based on how many minutes were left until their train departs. So in some, 85% of passengers would arrive within 10 minutes of their train's departure, but there's a little more granularity to that in the model. And then we also modeled 36 cyclists per train, which is a very high number, and that corresponds to 50% of the total cyclist capacity in the train. But again, this is just part of the stress testing. Next, looking at the pedestrian routing consideration. So one of the factors that we needed to consider was that 30% of passengers were assumed to need to purchase a ticket once they reach the station. All passengers need to validate their tickets before proceeding to the platform. And then there's also a waiting area that we needed to model where passengers would wait before proceeding to the platform. And then again, measurements that we wanted to look at included level of service, queue times, and platform clearance times. So a little bit about the initialization of passengers in the model. So the pedestrian inputs were manually coded, or the passenger volumes in the pedestrian inputs were basically manually coded on a minute-by-minute interval using this kind of matrix that we calculated that calculates how many of each passenger type will be arriving within which time interval before their train departs. So for the purpose of this, we had assumptions that within 15 minutes of the train's departure, 15% of passengers will arrive. Within 10 minutes, then 55% of passengers will arrive. And within 5 minutes, 30% of passengers will arrive. And so this was spread out across the different pedestrian types. For this model, all the pedestrian types act in a uniform manner. For the next model, we also incorporated variability amongst the pedestrian types so that, for example, commuter travelers would arrive later, closer to their train's departure compared to leisure travelers who would arrive earlier. And then when initializing the model, or at the beginning of the model, pedestrians are assigned a few attributes that guide their route decisions through the model. So they're manually assigned train numbers and then their corresponding platform numbers and departure times. From that, we get their arrival period, so how much time is left until their train departs. And then also there's a attribute on whether or not they need to buy a ticket when they reach the station. So this is the layout of the station. On the exterior of the station, there are 2 sets of pedestrian input areas, and then there are 6 access and egress points into the station. In the station, there's two sets of ticket vending machines on the north and the south side of the stations, and then throughout the station, there's 15 ticket validator machines. There's a waiting area in the middle, in the green, and then once passengers are called to board, they proceed to one of two platforms. So all trains for this model would arrive to one of the two platforms in the middle. And this is just showing how the pedestrian routing would work. So for departing passengers, they again would enter the station. If they are assigned that they need to buy a ticket, then they'd proceed to the ticket vending machines. If not, they'd skip those. And then if there's still more than 10 minutes before their train departs, then they'd proceed to the waiting area or the corresponding waiting area for their train, at which point they wait until they're called to board. Once they're called to board, they validate their tickets at one of the ticket validator machines and then proceed to the platform. The lighting flow is much more straightforward. They basically just exit the station. And this is just kind of a flow chart also illustrating that kind of a flow. Basically, the takeaways here are that there's two main decision points that dictate or that affect what routes the pedestrians take. So one, do they need to buy a ticket or not? And then two, how much time is left until their train departs. So now I have a demonstration. Oh, it's not playing. Was it? Playing on here, but not on there.
This presumes
Don't know how to do it.
I see it here. Maybe it's just delayed there.
No, it's gonna do some touch again.
She's done something with her laptop. I don't really understand what's happening. It's a video like overflow. You can't.
What happens if we like present it to your data?
So the last time we did this, we closed it and reopened it. That's not right. Yeah, there she is. Let's try that. I think what's happening is all the media is starting to overload the GPU for displaying it up there.
Mhm.
It's not a modeling laptop.
Yeah.
Every time I try to present this video, that box pops up, resume slideshow, and every time I click it, it stops the video.
The one thing that we can do, we can duplicate the screen. Okay, we can make it full screen. So. Yeah.
Okay.
That's why you're talking.
There we go. Okay, yeah. So this is the demonstration of the model run. You can see first two trains arrive, all these passengers alight, and then passengers start arriving at the station to board these two trains as they go back. People start to queue at the ticket vending machines. And then the first train's passengers are called to board, so they proceed to the platform, and then the second trains. So at this point, when we have all four trains on the platform, then we see a bit of the crowding start to really create a bottleneck. And also, especially all the cyclists did not help. Yeah, so it clearly starts to get really crazy. So as you probably saw, the station exhibited very high congestion with a level of service F. It was centered around that bottom corner area where there's a bit of a physical bottleneck. And there's also the ticket vending machines and the waiting area. So there's a lot of just conflicting processes going on. And because of that, some passengers experience platform clearance times greater than 10 minutes. So the takeaways from that, basically, we were able to make a few recommendations, including increasing the station footprint in the bottom portion where that bottleneck was centralized. Reduce the retail area footprint, which is labeled with the number 2 on the right side, to just open up the access and egress area. We also recommended scheduling trains to use 4 platforms instead of 2 here to spread out the passengers. And then finally, further down the tracks to add another pedestrian overpass, again, to spread out passengers for an additional access point. So I'll try to go through this one a little quickly. This is the second case study. This is for a new station design. Again, a intercity rail system. Similar research question, can the station handle projected ridership? For this model, we wanted to just look at average AM peak hour projections. So not looking at an extreme scenario, looking at a more normal scenario. And we wanted to evaluate level of service, queue dynamics for vertical circulation, as well as for fare gates. For this station, this is a through station, so there's trains going in both directions with 3 trains per hour per direction. Passenger volumes were set to projected peak ridership, which is 700 per hour. And here, as I mentioned previously, passengers were segmented by trip purpose. So we had business, commuters, leisure, and a few other categories, which affected their arrival times to the station, as well as their walking behavior, and their choice of vertical circulation elements. And then, yeah, so for the pedestrian routing, we had vertical circulation to consider, we had fare gates to consider, and then we had a waiting area behavior to consider. So this is a diagram of, or this is what the station looked like. So passengers start outside on the ground level. They have to go up to the concourse level using stairs, escalators, or elevators. Then they have to pass through the fare gates, after which they go and wait in the waiting area. 15 minutes before their train arrives, they are called to their respective platform to board, at which point they proceed again via the stairs, escalators, or elevators down to the platform level. Here's another flow chart showing the departing passenger flow behavior. So here the main considerations for route decisions are how are pedestrians going to access the station based on their characteristics, or based on their passenger type. So will they use the elevator, escalator, or stairs? So we have wheelchair passengers and cyclists, for example, who will always use elevators, whereas senior passengers would prefer elevators, and then everyone else will most likely split up between escalators and stairs. And then the other consideration is, again, how much time is there until their train arrives. If there's less than 15 minutes, they just proceed to the platform. If there's more, they have to go to the waiting area to wait. So I have a demonstration of the concourse level. So you can see passengers arriving, gathering in the waiting area. And then the northbound passengers are called to board. So they proceed to the platform. And then same for the southbound. And then here's a video showing the passenger exchange process when the trains are actually arriving. And here are a selection of some of the level of service results from this model. So overall, it was mostly just level of service A with little pockets of B and C, particularly in the waiting area when there'd be people waiting for trains in both directions. But overall, no crazy crowding. So based on that, we could come up with a few recommendations. One, maybe further study to optimize the waiting area configuration, as well as the platform access points. Two, is a recommendation to potentially reduce the station footprint in order to right size it to the ridership demand. And then three would be to perform more disruption scenario analyses to evaluate the robustness of the station design in more abnormal or high ridership situations.